So hello everyone, welcome to the final day of this workshop. For us who are online, welcome. So this has been an intense week, full of knowledge, full of networking, full of making friendships, and but today it's not going to be a less extraordinary day. So to finalize with this fantastic workshop today, we'll have SARProcessing, Datacubes, satellite data and reanalysis from Earth observation servers, and last minute session on the week's spontaneous outcomes. Amazing. So we'll start now with the plenary session, SARProcessing.jl, Vision, State of Affairs and Roadmap with Lippert, Simon Lupemba, Christian Sørensen, and Szczesniak. Since most of you were already presented, I'm just going to present my colleague. Iga is a project developer at the Earth Observation Lab of the Air Center. She holds a master's degree in geoinformatics, photogrammetry, and remote sensing obtained at the University of Science and Technology in Krakow. During her academic career, she worked with various Earth observation data and conducted research at Aalto University, Finland, focusing on the cryosphere, glacier monitoring, and SAR technology. Previously, she has analyzed the Earth observation markets and innovative usages of Copernicus Sentinel's data while interning at European Space Agency. Okay. Thank you.
Great, it works. Good morning, everyone, and nice to see you all again. Today we'll talk a little bit about synthetic aperture radar yet again, and most of you have already seen the presentation by either Felix or by Simon and Eigil, so hopefully all of you know somewhat what synthetic aperture radar is. So today we'll not go into much detail of the SAR sensors. Instead, we'll talk a little bit about the vision, the current state, and the roadmap of this SAR processing Julia package that we are developing. And currently we are 4 people working on the package, and since all of us are here in this very room, we'll all go up here and talk a little bit so you can see us all. And it's not only just a presentation of us, it's also like kind of an open discussion where we want you to actively contribute with a little bit of things or knowledges that you have of especially Julia. So first and foremost, these synthetic aperture radar images, as we recall, are these complex images with both intensity and phase. So they are actually very complex to process. I don't know if you can recall the workshop or the hands-on that Simon did with interferometric SAR. There was a lot of processing steps there. That's just one derived data product from SAR images. So there's a lot of processing steps in it. So it takes quite a bit. And so why do we then want to do it in Julia? And why do we then want to make SARProcessing.jl? Well, if we look at the already existing methods of handling SAR processing, there are quite a few, but they all have some disadvantages. And of course, what we'll do in Julia will not. But first and foremost, we have the commercial software that is quite expensive, actually. It's not transparent, and it's difficult to integrate in other processing chains. Obviously, there are a lot of algorithms where you can change specific parameters in these commercial things, but you cannot actually change a whole lot of the algorithms. And yeah, expensive. Well-known examples of these are the Gamma software for interferometric SAR. We have the consultancy Tre Altimira and MATLAB. MATLAB, you cannot even do all of the SAR processing in, so that's just also part of it. Then we have other non-commercial software, likewise not transparent, difficult to integrate. A classic example is the ESA Snap desktop that I think most people are actually using when they initially try to use SAR images. And while you can see a lot of the functions, you cannot, for instance, see the source code. It's buggy, it's slow, it's difficult to integrate and whatnot. And then we have different open source alternatives. And we have not yet seen a full processing chain of SAR processing in any of the programming languages that we know of. It's always where you have to like take bits and pieces from, for instance, the commercial software. And we also have that two-language problem that a lot of the things that have been implemented in, for instance, Python, is like using all the C implementation. A good example of that would be something that is called PyGMT SAR, which is just a Python wrapper for the C library, GMT SAR, and all it's doing is making interferometry. So to our knowledge, at least, there does not exist this, how can you say, open source framework where you can do the full processing of SAR data. This is what we envision in Julia. The vision is to have a full ecosystem in Julia for the full processing chain of SAR data. Now, when we say ecosystem and when we say processing chain, we mean something like this. We want to have some package. This is the SARProcessing.jl, where you can get the raw data depending on what raw data it is you want to get. You can do the pre-processing and you can get some kind of data that you can then use. This could be, for instance, the interferogram that we showed the other day. And then the ecosystem part here is also that it's very much indeed user-driven, such that we have a framework where you can get the data and you can make all of these applications yourself, and you can then contribute to the ecosystem. And it's here very important to say that in this vision, the SAR processing is just a part of the ecosystem. So processing is like obviously all of these things that you can see here, taking the raw data, processing it into data you can use. And then another part of the ecosystem could be all of these really, really neat applications that in truth is actually what people want and use, like velocity maps and deformation and all of these things. Moreover, we want it to be transparent, easy to inspect the source code and decompose the different processing steps. This is indeed very difficult in much of the external software. And therefore, we actually want to remove this need for commercial software, which is used a lot in SAR processing around the world, we think. We want it to not only be usable, but actually to be used for applications. Such that if you are a company and you are developing some algorithms, applications, we want people to use this framework. But we also want it to be an ecosystem where people are developing new SAR processing algorithms. In fact, that's how we see it being developed, because it's very technical to develop some of these algorithms, not only due to the software side of things, but also just the SAR complexity. So having people that knows a lot about SAR wanting to develop new SAR processing algorithms is how we move this forward. We want it to be user-friendly and in one language. No need for SAR, for C or Python or whatnot. Yeah. And now Simon will take over and explain to you about our current state of things.
Yes. So now we're presented a little bit about the vision and where we want to go with SAR processing, and also just building up a SAR ecosystem in Julia. I'm going to briefly touch upon like what is the current state of this package. Yeah, first of all, I think if you attended the hands-on session on Tuesday, you will have like a little idea of like what the state is. But the state is that we're somewhere a good place between a proof of concept and a finished package. So currently, this is actually just taken from the folder structure. But we have different parts of the SARProcessing.jl, and which part we kind of have involved have been motivated by the fact that Eigil and I, which is 2 contributors, we already had a part of some Julia code for doing interferometric SAR. So the vision was a little bit to go with that and to get something quite useful and quite advanced out in a relatively short time to show these capabilities. And a big part of the interferometric SAR is about the geocoding and stacking on top of it. It is like a fundamental process, and that's actually a place where we spend like a lot of the energy to get this out and get it in a state where we can show something. There's still need to go through some of these steps and like test them even further, especially like when we go to the INSAR part to validate that the results are correct. Talking about the sensors, we have previously worked with the Sentinel-1 satellite from ESA, and the data here are freely available and quite easy to access. So we thought that was like a good place to start with the sensors, but we have a clear vision of it being extendable to other SAR systems. So we're not making this package is not called Sentinel1.jl, it's called SARProcessing, and that's part of the vision that we're going in that direction. Coming up here, we have some object detector, speckle filter, and visualization. This part have really been like the visualization have been driven by all of us, and it's because building this package and developing it and coming here and giving a hands-on session, working with images, it's quite sad if you're not able to show any of the images. I don't know about how you feel, but just looking at matrices and numbers in 2D arrays get very tedious very fast. So we prioritize to have like a bit of visualizations in the package, but that might be restructured a bit later. Yeah, and then we have the object detection and speckle filter, and the reason why we started with those have been kind of twofold. So first of all, speckle filter and object detection is kind of like some fundamental things in SAR processing, which is used by a large part of the SAR community. That's like one of the justifications, and the other one is kind of the motivation with Christian actually using these processing steps is his actual work. So in that sense, it makes good sense to kind of prioritize them, so we can get a package we're able to use ourselves. These 3 points are combined in like one combined red box, and it's because we imagine that we're going to do quite some restructuring around this. So right now it's directly included in the package, but these filters and object detectors and visualizations, they really also depend on a lot on other packages, and some of it may be at an advantage to separate out in other parts of the SAR Julia ecosystem once it gets going. Yeah. And then feedback on the structure. So like this is our current state, and it's like just how we started to do it. And right now, all our works have been fused into to one package, and that's also been just to simplify the way to get started. but we really would like if someone has some feedback on like how to get started with structuring a package like this and get going. So I don't know if any of you see this and have some major comments. You're welcome to put your hand up now. Okay, that must mean it's not entirely terrible what we're doing, and we can continue a bit down this road. So that's at least some comfort. Okay, now Eichel is going to present a little bit about our roadmap.
Hello. Yeah, so we'll just show you a little bit about the more detailed, like close like a short-term future. So basically now we're working on the green, on like the first part is kind of now, and then you can see on the y-axis we have like Sentinel-1, and it kind of means because like currently we're only working with this sensor, so all the work we're doing it's probably working best for this. We hope it will be, of course, general, but it might have to be, you know, adapted to that when we start adding more sensors. And then we have something about the general structure. We have something about some additional methods and other stuff. And basically what we're working on now is also what you maybe got from the hands-on session if you attended that we are working on the INSAR and testing especially. And then also we're gonna have to do some restructuring. Oh, it's not. What's happening? No, okay. So is it? It's something. Okay, something. Sorry. I got distracted. Okay, so we have to restructure some stuff, and we will probably also work on doing like an interface for some of the things we're working on, and then we have some optimization. Then kind of soon we would like to start working on like downloading data more easily, because it's very useful for like end users. Basically you can make like API calls to download the data more like automatically. And then we'll start working also on the ground range detected products, which is basically, so what we showed the other day was like how you work with the phase of the image. But this is the work with the amplitude, so it's also pretty important. Actually, most people work with this data, so it's kind of very obvious to start working on this. Then in the, let's see, oh yeah, then below there is the general structure, and then we will start adding like other Julia packages for more functionality. We were talking about, for example, whether we should have a dependencies on the raster.jl, for example, for downloading DEM and getting that in a kind of common format, but some stuff like these things. And then you can see down the line, we have a hope to add the sensor ISI. I will come back to that in a second. And then down here, we see that over like the whole process, we hope to kind of help contribute to a general ecosystem. So the hope is that this can play a part in a kind of larger ecosystem around using SAR data. And this kind of consists of these 4 boxes, we think, both engaging the SAR community, and that's some of the people here that are already working with SAR. And then we were kind of discussing like how to get people to, because the difficult thing is like some of the algorithms in this field, they're quite complicated. You need actually to work on them or really know what you're doing to get it to work. But the thing is, most of these methods is already very, very well established. So it's neither research or like, it's kind of in the middle. So it's actually a good opportunity is to see if we can get students, like master students or something, who are interested in learning these specific methods to work on this basically, and hopefully they could contribute. That's kind of at least how me and Simon and Christian have learned a lot, and also Iga, I guess. I know just because I know Simon and Christian very well, but all of us have learned these things ourselves. So it would be kind of an obvious, I think if we can get some students to get motivated to add some of the more advanced algorithms. And then we also gonna work like very much focused on like who the early adopters are. So what is the need from the early adopters? could both be in terms of like default settings for like the data products, but it could also be in terms of like what we actually end up coding up. And then we hope to be able to empower the contributors. So a good example would be some master student has implemented a very basic algorithm or like a good algorithm in Julia, but it's not right package ready. It's just kind of a script or something. And then we can really help maybe, hopefully, to get them to learn how to contribute as a developer basically to the package. Yeah, and then hopefully soon we will also add this, like relatively soon, but like the next step, so to speak, is kind of add the sensor, the eye size sensor, and it will come in here in the package in the future. So basically, ISI is very high resolution SAR data, so it's very interesting for many people. And here you can see, I think it's a ship. Yeah, and you can see it's very kind of high resolution compared to the Sentinel-1 data. Do you have a comment? No? Okay, so Iga will just tell you a little bit about some applications. Oh, sorry, one thing I forgot to mention, the methods, sorry. It's just like the blue purple part. It's basically like in this ecosystem, because we will basically handle a lot of the data. So what will happen is also depending a little bit on like whether somebody will come in and build like persistent scatter interferometry in this ecosystem or something like that and want to contribute with that, then it will probably be another package, but maybe it will also kind of have to work together somehow. So we will have to see what happens. It depends a little bit like on what users will start adopting in this ecosystem, basically. Yeah.
Okay, so I'm gonna say a few words about the possible applications of the Air Center. So Air Center strongly support the SAR processing project, and we want to take an active part in the development and then in the actually use of the method and the package. As was mentioned before, SAR data are extremely computationally demanding because each pixel of the SAR image consists of information about the amplitude and intensity. So we see a lot of value in doing this work in Julia. A flexible package for SAR data processing will facilitate and greatly accelerate our data pipelines and the workflow in our organization. One of our area of application is persistent scattering interferometry. We would like to use the method for port monitoring to deliver millimeter scale deformation over large spatial areas like ports or airports. Yes. Another area of application is soil moisture content and estimation. We have one ongoing project about detecting fungus spores on the fields. We are working on finding, well, they occur when certain weather conditions occur for at least 3 days. We are trying to see if there is any correlation between the fungus spores and the soil moisture content in the soil. So this is also a possible thing to do with SAR. Then the last but not least, vessel detection. As you already noticed, probably, we are in the middle of the ocean, of the Atlantic Ocean, and it makes a lot of sense for us to track vessels and also the backscatter signal of a vessel is really good with SAR data, and we would like to use this information and include them to our projects at Air Center. Now we will go back again to the package itself.
Yeah, so we're just wrapping up now, and basically the one I also just mentioned in the final part was the user-driven part of the kind of the whole ecosystem. So for example, persistent scatter, speckle filtering, and differential interferometry, or object detection, which is some of the things that Iga just mentioned as applications. And these will basically be user-driven, which means that it's probably not so much us that will drive the development of these things, because we need somebody with the expert knowledge to do this. So actually, we are also like kind of wanting to put up out an open question. You're also welcome to, maybe if you get an idea later, to come and talk to us. But basically, how to best engage both the SAR community and going to Julia, but maybe also getting some people who's interested in remote sensing in Julia to get to work to SAR with SAR, but like how to kind of tackle this this challenge of having like both a very complicated algorithmic part in the backend, so to speak, and then also having people to go into Julia, which is a general, I guess, challenge in the whole community, right? To get people to adopt Julia in general, which I guess is going forward, but it's just, I guess, some people might have some experience. So if there's any input, you're very welcome to tell us. Otherwise, we are wrapping up and open for general questions as well. Yeah, so that's it. Thank you.
Thank you. Questions? Comments? Suggestions?
Felix has a comment. Maybe he needs the microphone. Yeah.
It's more from the other side. What things could you need from the JuliaEO community to push this forward?
What we could need from the Julia community?
Yeah.
I guess actually, I mean, what would be really nice, in my opinion, I think Simon agrees, and Christian Iga is related to this thing about the general structure of the package and some of the things we're doing. I mean, structurally, because it's the first time we build a Julia package, so we might be doing something horribly wrong. So it would be nice if somebody would give us a hint if that's the case. I don't know if you have any comments over there.
I think so already, like being here and just being part of the ecosystem, we already learned quite a lot that we'll go back and implement regarding like different packages. But yeah, I think we will need to we will need help in the future from the Julia community, again with the general structure, and then also like ensuring that we make kind of nice interfaces with some of the other common packages, so it becomes easy to use SAR processing to do some of the initial let's say inferograms and like derive some of the data, and then take this information into geodata frames or rasters for further analysis, or like once you get to the point where you're fusing it with the other data. From the SAR community, it would be nice to have somebody who wanna implement terrain corrections. It would be nice to have someone who wanna implement face unwrapping. It would be nice to have someone who would try to like. There's Felix, yourself showed a long list of SAR sensors. Integrating each of these SAR sensors in the package would also contribute. So in that sense, we can find something. Yeah.
And one more thing I thought about is like actually someone like yourself, Felix, if as soon as we are ready, if you start using the kind of package for getting the data you need, that'd be very nice, because yeah, then we'll figure out what's not working very quickly. Yeah.
There are two questions from the chat. What are the next sensors you are looking at, including, do they include TerraSAR-X and RadarSat-2?
What are the next sensors?
Yeah.
and whether they include TerraSAR X.
If you are planning to include TerraSAR X and the RadarSat 2.
Yeah. Do you have a?
So we would like to include all of them, but we cannot include all of them at this. I know we don't have the time to do it ourselves to start with. I don't think we took ISI as an example, but once we get to the point where we want to add a different sensor, it's very much driven by the need of the person who are developing and like the person who are contributing or some early adopter users. So we are open to having like a discussion about like which sensor to include in the chat, and especially like if you're really passionate about a sensor and you know a bit of Julia, you're welcome to become part of the ecosystem and contribute with an interface for that sensor. Personally, I don't have any like strong preferences to any of the sensors, but if a strong preference arises in the early adopters or in the contributors, of course, that's the one we're going to prioritize. We just put like adding a sensor, another sensor a bit early because it could also be a good way to kind of validating some of how flexible we have structured the package. So like making sure that it supports multiple sensors early on. But that's more from the architecture, the package architecture view, that it could be nice to have at least one additional sensor quite early, just to make sure that it is that the code is written in a way that supports multiple sensors early on, and not something we add in the very end.
Yeah, and then there was a question online about the SBAS interferometry, and currently we don't have any plan to do that, but it would of course be nice. And again, as this person online is saying, if it's interesting, it's very nice, because then we know that maybe it's something we can either work on or we can start working with this person online with. He's also suggesting some collaboration possibilities. So yeah, that's from the online, from the chat. Yeah.
So thank you so much, and very good. And thank you for sharing the roadmap. I think it's super useful to have this. Thank you for sharing. You mentioned the building of a community, a crucial aspect of this endeavor. I'm glad you're thinking about this explicitly. If there's anything that we can do to help as users of the package, we will certainly do our best. You mentioned also a critical element, which is architecture of the package. So we have Simon here, who's is the driver, the main driver of probably one of the largest ecosystems in Julia, sub-ecosystems within Julia, with Maki. So I don't know if he has some advice to provide at this stage.
So this is very far out of my domain. So I can't really judge it very well, but I think my biggest advice is just the community building. Go to the forums, ask a lot of questions, because I've always been super surprised how much feedback you can get and how many packages you actually suddenly pop up that are super helpful. And people just giving super helpful advices on how to structure things. So I think the Julia community and the forums are amazing, and they have been helping me a lot with Maki to structure everything. But yeah, I can't give any concrete input here because I don't really know the domain.
Thanks. Yeah, that's some good points. We can actually, I think once we have the kind of first sort of release, it's definitely something we should start pushing more for, like getting more in touch with the community, because we haven't done that so much yet. But also it's a bit easier, I think, when we have a little bit of like the basic stuff, because we actually did a post at some point, but it was like we didn't have anything at that point. So yeah,
I think it's also yeah, just being I think we will be more active on the forums going forward. It's always yeah, it's easily like to get the tunnel vision on like porting some code you have and doing and then forgetting. So it's really good advice, and we will take it up and start posting more things and more questions. So thank you.
Hey, yeah, so great stuff. I was just going to mention that so I'm involved with a few NASA projects and groups, and I'm sort of expecting that they're going to be quite interested in this. I'm assuming that you're welcoming everybody on their side to contribute, and I wanted to give you a chance to speak to that.
Oh,
yeah, thanks.
Thank you.
That's a good suggestion.
That would be really nice.
Yeah.
Okay, cool.
Thank you. That's it. Yeah,
thank you.
Okay, so that's time for coffee break. We'll be back at 10. 5 past 10.
Dois, três, três, dois, três, três. Dois, três, três, dois, três. Mas muito baixinho. Muito baixinho. Muito baixinho. Muito baixinho. Muito baixinho. Muito baixinho. Hã? Muito baixinho. Muito baixinho. Não é? Tá? Muito baixinho. Muito baixinho. Tudo no máximo. Tudo no máximo. Tudo no máximo. Tudo no máximo. Um, dois, três, três. Um, dois, três, três, três. Não se ouve nada, porra. Não se ouve nada. O que é que este som não está a sair? Hã? O que é que este som não está a sair? Sim. Por que este som não está a sair? Sim, está a sair?
Já estou a fazer o da taça aqui. Cabos, pois não é cabos, mas tipo. Deixa eu ver isso, as pontuações e não sei o quê. Tens que memorizar. Olha só para estes. Depois é para. Não, vai, já fiz a prática. Estou para ter saltos, os saltos de os símbolos. Não,
Ah, okay, okay, very good. Yeah, no. Good to tell you that to tell me now.
I'm going with you.
Okay, yeah, perfect.
Okay, everyone, let's proceed to the hands-on sessions. We are going to have two parallel sessions. The 1.1 will take place here, and it's entitled of Datacubes for High Resolution EO Data with Felix Cremer. And 1.2 will be upstairs. I'm going upstairs with Nathaniel Wong and Alexander Barth for the session called Retrieving Satellite and Reanalysis Data from EO Servers. Thank you.
So I would like to start. So unfortunately, the downloading of the data on a USB drive still takes some time. Iga, next to you, there's a hard drive. No, the large one. Yeah. There's at least the part for the second part of this hands-on session already on there. And I just let me have a quick look. So yeah, so I'm going to share this around. So there's this ESDC subset2.zar dataset on here that that we're going to use in the second part of the hands-on session. And I think for the first part, you just need to watch me doing it because yeah, I can't. The USB drives are too slow at the moment. Yes, of course. Hopefully. Like this? Is it okay? So yeah, I'm going to give an introduction to Azores and the processing of large data, and I'm also going to talk a bit about setting Sentinel-1 TIFF files up so that they can be used in Azores. And so first we instantiate our environment. They should be available on the apparently in the pull request for the JuliaEO GitHub, and so first we look into chunk data. So the data has to live somewhere on the disk, and so as Fabian mentioned yesterday, in geospatial data, we often have the problem that data that is close in space is not close on disk. And therefore, depending on your use cases and on the analysis you're doing on the dimensions, you can have certain data to, you can have problems because there's some access penalty, and we're going to look into this if you load a netcdf file. So we're using the netcdf package here, and then we're using disk arrays to look into the chunking sizes of the data. And so we now have a compressed netcdf file with a size of 1440 by 720 by, so this is the spatial size, and then we have 1794 time steps, and the chunking is as maps. So it's one map, and then it's the next time step, and it's the next, and so on. So therefore, it's very fast to just access the single time step and the whole spatial pattern, but it's very painful to access the whole, just access one time axis. Because the problem is that the computer needs to access every single chunk of your data set. So this is roughly 5 GB of data that is then just accessed all at the same time, and it has to decompress the whole thing, and then it has to load just takes the one time step and then has to decompress the next chunk and takes one number. And just as a comparison, I have the same data chunked in smaller spatial subsets. So it's I think it's a chunking of 90 by 90 by 184. And there we see that the chunking of the maps is a bit slower, or it's quite a lot slower because it's some orders of magnitude slower, but the access of single time steps is a magnitude faster, two orders of magnitude faster. So here with disk arrays, we can have a look into the different chunkings, and so with this each chunk, you get basically the indexes into every chunk, and so we see here that the chunking is like the whole map in lot and longitude and latitude, and then a single time step. And then disk arrays knows this internal chunking structure, and therefore can implement special MapReduce functions that can then be used, for example, for the mean. And you can see that even though so this is going to take half a minute, but even though the access of single time series is very slow, the MapReduce over the whole time axis has a similar speed, because it's accessing every chunk once and then making sure that you're doing the MapReduce over all pixels at the same time. And then so this works quite easy for the mean, but it's not as easy for the median, because to compute the median, you have to have the whole time series in memory, because it's not a MapReduce, I think, anymore. So we can see here that we can take views into subparts of our spatial grid, and then this is very slow, because it has to do a lot of these deep compression and access patterns that are not fast. So it would be better to just do to always read a certain size of memory, and then just do all the computations on that memory, and then read the next chunk. So we can here just define the latitude ranges that we want to do, so that we have a certain amount of memory loaded at the same time, and then you can do this MapReduce over these latitude ranges at the same time, and then compute that for these multiple steps, which makes it already a lot faster. And so this is basically what what I should have done. This is basically what Azores is doing in the background. So it's making sure that your computations are done efficiently for these very large data sets. So here we have this the netcdf file loaded as a JuliaEO data set, and then we can access this layer, the one layer so that we can just load the data, and we see that this is a JuliaEO with the longitude, latitude dimensions, and 1,748 time steps, and then so this total size is basically the maximal possible amount of data that would be there. So it's just the product of the sizes of every dimension times the size of the element type. And so we can see here that this this is doing a map slices of the median. So it's just apply the median on every slice of data. And for the slicing, we're using the time dimension. So here you can specify these dimensions as strings, or as named strings, or as axes in the in your JuliaEO. And we see that this computation is taking roughly a minute, and this is basically what we with the naive approach of just, where was it? Doing this with the view. It's taking the same time for the whole data set as it would have taken for a 4x4 or for 4 grid cells. So it's a lot faster. And then it's also taking care of the parallelization. So it's using the distributed package. So that's the standard library of Julia, and it's using so here we just add some processes to do the to have some workers to parallelize the data access and the computations. Then we have to make sure that every package that we're going to use is available on every worker. And then we can do the same operation, and now JuliaEO is going to use all of the available workers because they're available in the background. And I don't know why, but this is failing for me in this Jupyter notebook at the moment. I didn't find the error yet. But it's definitely worked in my normal setup. It works quite smooth, and then you can even use different. You can use Slurm or other cluster managers to access or to set up the workers, and then it's going to take care of the workers. And then so because of this, because the data set access is so painful, it might make sense to rechunk the data if you're going to use the same patterns over and over again. So if you know that you're going to use this data set as a time series or for time series analysis, it might make sense to pay this chunking cost once and save the whole data set in a new setup, in a new chunking, so that you can then have more streamlined access for the whole experiments that you're doing later on. And to do that, you can use the set chunks function, which takes your data set and then it takes a named tuple of chunk sizes for every dimension in your data set. And then this is still lazy, and then you could you can then save this as a SAR file somewhere on disk. And now for that, I mean, this is now a compromise chunking of, okay, we don't have every time step, but we also don't have just the whole time series for very small spatial regions. So it's just, it's an in-between compromise, but I'm also using a lot of the whole time series and then just a smaller or smallish spatial region in my daily work. Should be that, right? So this is so this should show a progress bar now, hopefully. So yeah, you see here it's Are there any questions so far to the chunking while we're waiting for the computation to end? Now you see that this was a bit faster than so this took now on the chunk data took 51 seconds, while just doing the whole thing here took 1 minute and 16 seconds. So it's a reduction of 25 seconds. So it's a bit of a reduction for this data set. I mean, yeah. So it's always interesting to think about what are your best, what's the best compromise you would get to do all the analysis you're planning on. Yeah. Okay. So for the second part, unfortunately, I forgot to wait. Maybe I can. Let me check whether I can just copy these data sets into your USB drive, so you might be able to follow along. It's done already. Okay, good. So the next part is about combining multiple TIFF files into a YAX array, so that you can then continue working on them. So my use case was having sent a lot of Sentinel-1 data that was already pre-processed, and then combining that into a spatial cube. So you have a data cube of longitude, latitude, time, and polarization. There's a folder with S1 data. And I just realized that I should get my charger cable, otherwise it's going to be ending soon. So to work with the Sentinel-1 data, we have this folder S1 data. And then we just specify a polarization. So we first want to do this on the VH data. And then basically these lines are just to walk through the folder and find all data that is, find all files that have this polarization string inside them. So I assume that the data is all following certain naming pattern, and then I'm just filtering for the data that has this VH here. So this is so we have a few metadata in the file name already. So it's the sensor type, it's the acquisition mode, it's the orbit, it's the time of acquisition, it's the orbit number, it's the polarization, and then it's some pre-processing steps. And then I'm going to first pass the data from the time information from these file names. So you can do the get date, and then you search for these patterns of the year information, the month, the date, and then the time stamp. And if we do that, we get a vector of datetime objects that say, okay, this is 3rd October 2016 and 16th of January 2020, and then some timestamp. And here you see that these timestamps are really really near together. So it's basically it's the same acquisition, and and then it's another acquisition 2 years later, or actually 4 years later. And so as a precautionary step, I'm going to sort the dates by time, and also the files, so that we really know that we have a sorted time series, because before the data has been sorted by just the path, and this might be failing. And then we're grouping the data into different times. So we say, okay, we have a time difference of 200 seconds. So we assume that everything that is just 200 seconds apart is just going to be actually the same acquisition. It's just going to be split by ESA because for the data handling. And now we are going to use the GDAL VRT system to just combine multiple, to combine them spatially. So to do the mosaicing, and to do that, we first define this temporary path where we have a path for every subgroup of the data, and then we save the data into VRTs. Okay, wait, I did not. I did load that, no? Now this should work. Now you see that we have these interactive data sets of ArchGDAL. There's the information of the input data, and so we see here the data set width and height in pixel, and some metadata information. And now we build now we save these, now we build these VRTs for every subgroup. So it's this, so now we're spatially mosaicing the data together. Now we have a set of, so we have a vector of 2 ArchGDAL data sets. So we have one for every time step. So there's a, and in every data set there's this, okay, we have one file here, and we have these two files together that are basically just near each other, and then we have the other time step with the same setup. And now we can use this GDAL build VRT with the separate keyword, just to say, okay, keep everything separate in separate bands. So otherwise, VRT would, or GDAL would try to mosaic them together spatially, or just averaging them. And here we say, okay, just group them next to each other and keep them apart. And now we have this raster data set of ArchGDAL, and now we can use YAXArray to just the YAXArray type to convert it into YAXArray. And now we only have this band information, but we already knew the dates that we used for that. So we have these, so we just take the first time step of every subgroup, and then we construct a time axis here with these dates, and then we can just use this axis in our cube, so that we then have a the whole that we have now a data cube of the 5 of the latitude longitude by time axis. And this works as well if you would have a lot more data or a lot more time steps that you would like to put together. And now we can see that we have this cube chunks. So we can check, okay, what's the chunk size of the data set, and now we see it's basically similar to the problem we had earlier. It's a very small, it's a small spatial chunk, and then it's just one time step. So because And that's because they basically all came from single TIFF files. And now we can use this the set chunks function again to say, okay, we want to have we want to have a chunking in space, and then we want to have just have the whole time series. And that's what we're doing here. And then you see, okay, the new, this is the new chunking. And then now you can use SafeCube to say, okay, and now I'm going to save this into a ZAR file, and then we can use that to do our further analysis and work with it later on. Or you could as easily replace this by your .NET CDF, and then it would then it would also just use the NetCDF backend to write the data to. Okay, are there any questions about that? Or is it all clear? Okay. So then I'm going to give a general introduction to Azores and the MapCube function. So I hope that at least some of you now have the EastDC subset 2 ZAR file on your computer. No, it's there. Okay. That's a bit of a shame, but I mean, we can try to use the maybe we could try to just use the Earth Data Lab. Yeah. Yes.
How do you normally decide the number of chunks you want? It's very dependent on like what you're processing, and is it heavy to like re-chunk the data when you figure out you divide it like wrongly?
That, I mean, yeah, yes, because it's basically, I mean, you need to touch the whole data set again for the rechunking. So depending on that, it's, I mean, with the data set I'm normally working with, it's okay because it's small enough. But for larger data sets, it's just getting more painful. And so I would say it depends on the use cases on the analysis you want to do later on. So the aim of the chunking is to put data together on the disk that you're normally using together. So if you're mostly doing spatial analysis or spatial averages or something like that, it makes sense to have them together. So to have a larger spatial size, chunking size. I'm using mostly time series, and I'm mostly using the whole time series at the same time. So for me, it makes sense to just have a chunking that is rather small chunks in space, but then the whole time series. And I'm also not too sure about good heuristics to find the perfect chunking size. We're planning on looking a bit into that. So seeing how, I mean, it also, I think it might also depend a bit on your general computing setup. But so you don't want to have too small chunks, because then you would have to open too many files all the time. But you also don't want to have your chunks too large, because then it's just not feasible, because then you have to load them all the time, and then they are just too large for your memory. And then depending on the analysis you're doing, whether you have how much sub steps you have, because normally you're not only loading one data set, or you're loading your data set once, and then you're doing computations, and you have temporary results that are of similar size some of the time. So that's also something. So you don't want to be too large, because then you will blow up your memory. So yeah.
But it's quite easy to rechunk. Okay, it will take time, but there's functions that the documentation.
Yes.
It's one line. So it's one line.
It's easy, but it might take some time depending on the size of your data. That's just.
Yeah.
And I mean, there's also use cases. I mean, for example, for this Earth System Data Lab that we are.
It's not like you're rechunking data set between changes. Oh, I computed this format, and then I need to do some other.
No. What we did for this for the Earth Data Lab, which is a huge, so it's a spatial chunk. So it's a global data set of a lot of different variables, so climate and other things, and because you have this cost, they are available in both chunkings.
Oh, okay.
So that's another way you can deal with that, basically, but by just paying disk size. Yeah. So just basically blow up your whole, just double your disk size of the whole data, because you're just going to do this again. And there are even I'm not sure what the status of this is at the moment, but there was an extension for the SAR specification of having multiple chunkings in one file, which would help, because you can then have the same compression. So the data could be compressed together, because it's the same data, it's just different chunkings.
Yeah.
And
okay, this leads to a slightly different question. Just out of curiosity, is it possible to have like irregular chunking?
Yes.
Okay.
Maybe Raf can say a bit more about that. Yeah. No?
Okay. Exciting.
I'm not sure why updating the registry is taking so long at the moment, but if you don't have the data and want to follow along at least a bit, you can use the EOS Data Lab package and load the ESDC. So it would then be just but I'm going to continue a bit, and then no, I wouldn't. Oh, okay. What? Okay, yeah, that's not working at the moment. Okay, it's not. So yeah, that's so we're now looking into this. So we're just using this this data set. So it's a subset of this system Datacube that you could get from the EOS Data Lab package. We're just doing C equals ESDC, and this would be hosted on the on our cluster in Jena. And but here we have this data set with 720 by, so it's again the latitude longitude grid and the same time steps. And here we have different variables. So we have air temperature, land surface temperature, GPP, yeah, so it's just 5 of them. So we want to do construct a cube out of them because they have all the same grid. So this is the main difference between the data set and the YAX array, is that in a data set you can have multiple subcubes. So you have multiple subcubes and they might have different dimensions. So you could have one cube with latitude, longitude, time, and then another cube that is just the static information of land cover, for example. And with the cube function, you just convert the whole data set, or you try to convert every variable that has the same dimensions and put them together in a data cube, and then you have this new variable dimension which has as access these cube names basically. And here you see that the size would be 33 gigabyte if you would load the whole thing into memory, but actually this could include missing values. That's not that in the end, but it's and it's also not as large on the computer. So on the computer, this is now just 5 gigabyte, but it could blow up to that. And so this is just a lazy representation. And now we want to do some computations on that. So we have this map cube function, and so the map cube function takes this inner function. It takes the input cubes, it takes the input dimensions and the output dimensions, and so the inner function always has the structure of x out, so the output, then the input, and then you can have other variables or other keyboard arguments. And here we're just applying a median, so we're filtering the nuns, and then we're just going. Then we see just compute the median if there is some time information there, which was not none, all none. And it's important that you always, so it works that by just updating this output variable, so it's doing the computations in place. This makes it faster because you can reuse the memory you allocated for different chunks. You can reuse them all over again and again. And why is this taking so long? Okay, I think this is taking now some time because I don't have any threads or any parallelization going on. So it's interesting. Okay. Oh. Okay. Here we run into the problem of apparently having missing data. With that. The problem is that apparently in this data set we have missing values and none. So we have to filter for both. Otherwise, it's not going to work at all. Okay, that was not it, I think. Damn it. I'm going to try it one last time and then I'm going to move on. Because I don't see the yeah. Okay, so I think it's now working, but I'm going to move on and explain the next step while waiting on this computation. What actually? Next. Okay. So with this map cube function, you can also combine multiple cubes or have an output of multiple cubes. So the idea is that so here we have multiple outputs. So we have a time series output, we have a mean output, we have a standard deviation. And we have one input. So we in this example, we're computing the normalized time series by subtracting the mean and dividing by the standard deviation, and while also saving mean and standard deviation of the whole time series. And so here you see, so in the inner function, you have these multiple outputs, and then you have to make sure that you're assigning values to these outputs. And then you're computing, so you're updating these, and then you can update the mean by the mean function and so on. And to define this in the map cube, in the outer map cube, you define one input dimension. You say, okay, I want to input time, and then you have you have multiple output dimensions for your different outputs. So you have the time for your whole time series, and then you can specify a path where the output data is saved, because this is all going to be loaded chunk by chunk. So it's doing the computation and it's saving the computation per chunk somewhere. And so if you don't specify this is going to be in some temporary folder, which is going to be deleted later on. But if you specify this, you can specify the exact location where the SAR file that was computed is going to be saved. And you can then also specify the back end, and you say, okay, I want to overwrite whatever was there already. And you can even mix different backends in the same mapcube call. And so you have this, so have the means and the standard deviations, and save them in netcdf. And then you just have a tuple of output dimensions. And here you say, and then you get back a tuple of cubes, and these are then computed. And here you see that the outputs are a cube of the same size as the input. You have and then you have two cubes of where the time dimension is just reduced. So it's you lose the time axis because you have reduced over it, and it's just going, and it's going to do this computation for all your variables, because you didn't specify the variable axis. And I'm not going to run this now because somehow my setup is really shaky. I don't know why. And so far this was all just some statistics, but you can basically run every Julia function that is available on a YAX array. So you can specify some user-defined function, and then it's just going to apply this over all the input that you specified. So we want to do some, so we could do some time series decomposition. So here we have the it's the GPP over time, and that then you can separate this into a trend component, a seasonal component, and whatever's left. And when we now want to compute this, we have the input dimension. So we specify, okay, use it on the time, and then we can specify the output dimensions. And here we are basically we're computing from one time series, we're computing 3 time series. So we are increasing the size of the dimension. And so therefore our time, our outdims is the time. And then we can specify a categorical access. So it's just a new access to save these different time series, and we can give it a name, and we have the scale. We just call it scale, and then we have the we have a vector of dimension names. So it's just seasonal, trend, and remainder. And here again, we can specify the path and the backend, and then we specify these the inner function. Again, it's just x out and x in. So we say, okay, if any of these is none, we're just returning missing, and then we compute this time series decomposition, and then we save them in the different slices of the output. And I'm there to run it again. Do you have any questions so far about the mapcube function or the Azores functionality? Yes. Wait for the mic.
Yeah. So the functions you've shown here mainly like collapse, or like you go along one dimension, but how is it like applying a window in one of the dimensions? So
might be coming to, oh, no, we didn't. Okay. Yeah. I can show you that. It's actually quite easy. So you want to implement speckle filters, no?
Yeah, so actually there's I one time saw an article about a spatial temporal speckle filter, where you look at a window in space and then also a window in time.
So
or
what
something.
you can do is
Maybe that would be like the advanced case.
So you can do speckle.
Yeah, so something like a local mean in both space and time.
So it's just a mean, right? It's actually it's just like so you could do something like that. I mean, you could do a lot more of,
Yeah.
I mean, in regards of kernel, but then you would have a And then you can, so you have this moving window type, which can be used for the setting of the dimension.
Yeah.
And then you can specify, you can even specify the so
yeah, the size.
The size in both sides. So you could say, I think 5 days before and 0 afterwards.
Okay.
So you can have shifted moving windows, or you can have unequal moving windows, and then you can do I think. And then if you just specify, if you only have so if you only specify one, it's going to be quadratic.
Yeah.
It's basically the idea of like, okay, just let me interrupt this computation we tried earlier, but and then see that whether this is actually working. Wait, what? It's not. Okay, maybe I was misremembering that this works, but it should. And now we should do map cube of S1. We loaded the Sentinel-1 data earlier, right? So we can do yeah, dangerous live coding, but okay. Yes, I didn't rename the data earlier, so this should be X. This should be Y. Okay, and now it's up to
the missing values.
Missing values, filtering. I mean, now you would have to basically do the more special things in your inner function. That's just the idea of this moving window of these moving window things.
Can you try and go up to the filter mean filter? Just
wait.
Yeah. So here the xn the size of xn would like correspond to the size of the moving windows, like, and also the dimension.
Is it not showing? Yes, so the size of the size should be 5 by 5 by 9 by 9.
Okay.
Or 6 by 6, right? Oh, wait. Yeah, I'm not.
Yeah.
Yes, and then you can also, so it's normally just loaded as a plain array type, but you could do it, so you could specify the R type. So I think it should be here, like this. You can say, okay, I want to have an Yax array in the inner function.
Okay.
Because then you can have a, and then you could use the same functionality. I mean, I think it would not be that fast to then also use mapcube in your inner function, but at least you would know the dimensions.
Okay.
And so on. So you would have a named dimension. Yeah. I'm not too sure how good this would work then, but at least it's possible, and it's like sometimes it's nice. I think it's going to do a new size, so it's not. I'm not sure whether it's going to inherit the X and Y coordinates from the the position, rather like 5 till 0 to 5 or something like that. But it still has the dimension name.
All right. Thank you.
Then another thing that we can that we provide in Azores is this cube table interface. So it's just converting your data into a table, and then you can do certain computations on that. So something is not right. Okay. So here now we have a the data set we had before, and we also have a data set with all the country information. So it's just it's a rasterization of the countries of the world, and now we can construct a table out of that by just saying, okay, cube table, and then this is going to be the name, and then you say, okay, I want to have this variable represented as GPP in my table, and I want to have air temperature 2 meter represented as TR in my table, and I want to have the countries the other country file represented as country, and so you can combine multiple cubes into one table. And so you get an iterator over subtables. So this is going to be a bit nested because it's all taking the chunking into account. So it's being these, I think the 78 subtables represent or are aligned to the chunking of the data set, and you can then access one of these subtables, and you see that you have this schema. So you have a GPP, TR, country, and then you have the longitude, latitude, and time information. And this is all lazy, and you're going to only load the data as if you would access it. So now we have a subtable, and then now you see that you have a you access all of this of this temperature information, and you can then convert it to a data frame or something else, because it's all implementing the tables interface. So every subset is a tables interface, or every subtable is a tables interface. And now you see that you have this huge data frame of this data frame of GPP, TR, and then the country. And now you can also do computations on these tables using the weighted online stats or the online stats package to do some aggregation computations. Now we again, okay. I shouldn't have tried to use multiple processes. This does not want to play with me today. Yes. Okay. So let's not do that. Let's just do this. So yeah, while we're loading on it, I can explain the next step. So the idea is to have this. So you have this cube fit table function that takes a cube table that we constructed earlier. Then it takes a weighted online stats aggregation method or type. And then you can say, okay, I want to fit the air temperature. And then you can specify, okay, I want to fit it by country. And I weight by the cos d of the latitude. And I don't dare to do that now because I assume it would take quite some time if it took a minute with multiple processes. So so by this you get the mean by country for every, so the mean air temperature for every country weighted by the size of the degree pixel. So that's basically the idea. And then you can, and now you can basically then convert this to a data frame to look into this and see that. And you can also do it by time. So you can have this. You can basically say, okay, I want to split it by months, and then you can say, so you would get not only one value per country, but you would get a value per country per month of the year. So it's now the average monthly average air temperature, all with a weight. And you can then also and you can use at least some of the online stats functionality with that, and all it's all quite fast because it's online stats, so it's only using so it doesn't have to load the whole time series before doing the statistics, but it's doing that as on the go, I would say. So, of course.
I was just wondering whether the weights, I see here that you provide them as a function of latitude. Can you provide them in the form of like a data set itself, like either a column in a table or an array that you would index into?
I think, yes. I mean,
maybe it's not specific to your package really, but the weighted average.
Basically just that's a good question. Yeah, I mean, you might have to jump to some hoops there to
okay.
Just but I think what you could definitely do is you could load your data into your subtable.
Right, that's I was thinking, yeah, essentially adding columns to
you can basically, I mean, you here in this cube table, you're specifying, you can, so this whole example was starting here, right? So here we have just the data set. So it's a global data set with with multiple variables. Then you have a rasterization of the countries, and then which is rasterized on the same grid. And then you have and then now here you can specify this cube table, and then you can say, okay, I want a GPP, and I want to, and then here you rename the things again, and then the countries, and then you could have here your own weights.
Yeah,
I think
makes sense. I think it'll do it for me. Thank you.
That should work. Yeah. Are there any other questions? No? Thanks, Simon. Yeah.
It's more just now. So like, what is the big features that you're working on now, and like where do you see it, like it going? What are the challenges?
So I think so the next step is basically getting rid of our own or moving our own cube type to the dimensional data thing. I think one of the things on the agenda, because it would be nice to have this overlap of, I mean, Rasters is doing a really good job in providing all of the indexing features, and also getting stuff on the GPU. And I mean, that's just different focus areas that we had, and we are more focused on really larger data and trying to use that. So it would be nice to just combine these efforts and try to get our, so I think it's clear that our data cube, our Azores type is just not as good as the dimensional data things. So that's a step. And then Fabian is currently started to work on a rewrite of the whole backend of. So I think the idea is to have everything as moving windows. So the idea is that to just have one streamlined interface, or like one implementation in the background that's just doing the moving windows, and then you, if you want to have the whole time series, you just set your moving window size to the whole time series, and then do the computation then. I think these are things that we're currently working on. In the long term, I would like to explore more in combining good information more into the computations, and see whether we can basically see that you only do the computations if your grids are aligning, or you also do the resampling only if it's necessary, and go more into an abstract computation thing on some of that. But that's really further into the future. Yes.
Yeah, I was going to ask a question you might have answered earlier, and if I was distracted, I'm sorry for that. But was wondering your performance if you had sort of benchmarked your package against, I think the Python solution would be something like Dask and Accelerate together.
Mm-hmm.
Do you want to comment on performance or benchmarking of that?
I haven't personally did a benchmark yet, or not these. I mean, that's also something that we should be doing, to actually know some of that. From what I heard is that some things are not possible on Accelerate and Dask, at least have not been possible, because especially in the combination of like spatial and temporal together, or doing, I think one of the examples was doing a PCA for every pixel and then over the whole time series. The problem is, I think, I'm not really sure about this, but I think some problems arise because Dask is trying to compute the whole computation graph for every pixel. And then if your data is large enough, it's just going to fail. But yeah, I need to have more, actually to properly comment on performance differences, I would have to actually do the computation or the comparisons. So we have not done that.
Okay, thank you. Yeah, I would like to highlight that this is very important in that way, what you're doing, because that's one of the workflows that the Python community really wants from us. And so I think this is, this is really important work.
Are there any online questions? Okay, if there are not any more questions, then I think we can just close it, right? Or is there? Okay. Then we close the hands-on session for now. Okay, thanks.
Hello, everyone here and online. What a week. Well, so this is the closing session. If you are online, you also notice that we have a session that is not going to be recorded in the afternoon. This was a special request from the attendees here that have been hacking away and want to show the future. These presentations have been about the past, about the things that exist, and now later there will be a small surprise for those who are actually here. So sorry about that, but it will be it won't be recorded. So thank you very much for coming. It's a small message now from me, from Gail, and then we have the presence of the CEO of the Art Center, Emir Siraj, here as well, who's going to also say a few words. So thanking everyone, and then a bit of content about the feedback form. We are going to circulate over email a feedback link to those of are online, to those who are here as well, and to the speakers in particular. And we really appreciate if you could fill in that form. I know that it will just take a minute. It's not, I mean, you're busy, I know, but it will be very helpful. And it will especially help us with preparing new sessions, in particular the new session next year. So that takes me to JuliaEO 2024. This is a save the date announcement. So we are really planning to do this as an annual event. Next year, we're discussing where it should be. Location is not confirmed. It's up for debate. It doesn't have to be here. But the week should be this week, 8th to 12th of January. We discussed a lot of stuff this week. We had a session about an introduction to Julia. So if you are a developer, that will get you familiar with all sorts of things that are done slightly different in Julia. We had an incredible session about plotting. We had examples of working with raster and vector data. We had sessions about ocean modeling. We had SAR and also optical satellite-based data manipulation, processing. We had LiDAR data. We discussed that as well. We had high definition Datacubes. We talked about Datacubes with Julia, satellite data retrieval, just a fantastic session just now from Nathaniel. Had machine learning with geospatial data. We had geostatistics, and I could elaborate more, but you know the content. I'd like to also thank everyone who came. Some of you came from pretty far, and I know that it involved taking flights, and we don't like doing that nowadays. But I think it was worth it, and I hope it keeps being worth it to also be together sometimes to do things that are harder to do when we're not together, and to come up with new ideas like has been happening this week. From the support staff, I wanted to thank especially to Katarina. She's done an amazing job. I know all of you know that by now. Mariana Avila also for introducing the speakers as well. And then the support video crew, Surplus, and then I help with the microphones here and the flash drives from Raej, from Sonuno and Elsa. And a big thank you to all the speakers and all the ones who intervened here, who participated actively, but to the speakers in particular, Alexander Barth, Igor Lippert, Fabian Gans, Felix Cremer, Gail Forge, Julio Offiman, Lazaro Alonso, Martin Pronk, Martin Visser, Milan Clower, Nathaniel Wong, Raphael Schouten, Simon Danish, and Simon Lupemba. fantastic presentations, super high quality content. We've demonstrated a few things. First, we showed the state of the art of JL in Julia. And we also showed very clearly, I think, at least I'm super convinced that Julia's ecosystem is perfectly ripe for Earth observation. And the fact that Julia can help us use the new hardware, for example, GPUs, is a game changer for Earth observation, I think, because it allows us to do things we never thought possible. Things that could take months to do, we can now do much, much faster. And this allows scientists to actually do real applications, live applications, and we can leverage the power of Earth observation much faster. A big thank you as well to all our sponsors. As you know, the EO lab from the Earth Center is a lab Azores. So we are an ESA lab, and therefore this is an ESA event. But of course, thank the Air Center, the government of the Azores through the EMA-Espaço, the special segment from the government of Azores for dealing with space issues, the space strategy of the region, the MBON, Marine Biodiversity Observation Network, for also sponsoring, and we dedicated pretty much a full day to MBON with a hackathon as well. And there was a lot of ocean modeling, the sea biome, and thank you so much. Gail was an instrumental person, part of the organizing committee here. We met here actually in this hotel, in that balcony there in July, and that's how this idea popped up, and we've been working on it every week since. So thank you very much. And to his laboratory, Sea Biomes, of course. The Foundation for Luso-American Foundation for Development, which supports activities in particular between Portugal and the United States. They also sponsored this event, and Angra do Egoísmo is also a sponsor of the event. You had the opportunity to have dinner with the mayor of the city, and it was a good dinner. I know you enjoyed it. So this is all I think we can say for now. Thank you very much once again for coming, and we hope to see you again soon. Now Gail is going to say a few more words, and then we're going to have our student.
All right. Hi, it's me again. Well, I thought, what a blast, right? And I'm going to echo a lot of what Joe just said. I think this week, collectively, we've built up a community that was there and is growing. I'm very excited to see how far we've come already with Julia and Earth observations. And I'm, looking forward to how far we are going to get in the coming months and years. In the short term, we expect to bring updates to JuliaCon 2023 this summer in Cambridge, where I expect to be myself, and I think we will have Joe and some of his team as well. But I feel, the benefits of this week were already obvious, like the in-person interactions this week between people that were new to Julia and those more experienced, but also between the developers that don't have so many opportunities to spend time together. All of that was very, very positive and fruitful, I feel. So to sum up the workshop in a slightly different way, I think it provided a collective demonstration that Julia is not just the language of the future as far as Earth observations is concerned, but it's also the present, essentially. And it's, we have already, I think, a software environment, but also a community that is highly competitive and thriving. So I'm quite pleased with the work we put in and the outcomes of this meeting. So thank you again for all of you to be here, all of the attendees, especially those in person, It's been my privilege to meet you all, for those that I didn't know, or to meet you again, for those that I did know. And also for all of you online, thank you all so much for attending. So we hope that all of you that attended are even more convinced today that Julia is good for you, and look forward to what you'll do with it. On the sponsors, we've already thanked everybody, but I will specifically thank the Air Center for driving this event. Without you, this would not have happened, evidently. Mborn, and close to my heart, Sea Biomes, and the Simons Foundation behind it that sponsored my contributions. And to all of the speakers, it's been really, really good to meet you guys. For those that I had not, it's been awesome to interact in person specifically, and to see all of the spontaneous hackathoning taking place. I think collectively, like I said, we have consolidated a community that's very inclusive, friendly, and fun. So come join us, all of you out there. And I think we've also shown that Julia is basically competitive for this today, with any other open source effort in my mind, at least those that I know of. So in summary, thank you all, great stuff, keep at it and enjoy. And finally, thanks to my partners on the organizing committee, Andre, Iga, who did a ton of great work on this, and Jao, obviously. Look forward to more. And again, also Katarina and the AV team, thank you for driving this so efficiently and helping us deliver such great product. Cheers.
So, good morning, everyone. Some final words. My name is Emir Siraj. I'm the CEO of the Air Center. So, welcome to everyone. It's an honor to come visit Terceira today and see so much of an international community around the table. Today, the Air Center is around 22 countries, 85 institutions. I see here Cabo Verde, Brazil, many other countries, certainly from the Atlantic, are around the table. João was telling me it's a long list here, presentially and online. So the Air Center is all about this, is about joining communities, expert communities. We are integrating, as you know, disciplines in ocean, in space, also data sciences. I think this is a reflection of this success. It was already said by João and Gael. I think a big thank you to you both, as you met here in July and you connected to create this event. This is the start. There is a long way. João announced already the second edition of Julia workshop. And I think it's very important that from today until the second edition, this community continues to work together, continues to engage together. It's very interesting to see how this language then is being applied to a market around Earth observation, where science is very important, but also the private sector. And I know that one company is around Geosat, is participating. I hope to see in the second edition more companies that are working in Earth observation and maybe connect here with the community to really tackle use cases that in the end are important to certain user communities to solve problems in agriculture, in fisheries, issues about, as you know, ocean pollution, plastics, and so on. So there's a lot of problems, a lot of challenges. And I think this community is an example that from these solutions can be made, and you can make the bridge between science and the companies. Coming back to the sponsors here, and I think I'm not going to mention, a big thank you to all that supported this workshop. I hope that in the second edition they will maintain. Also here, the EMA Espaço is here, and the regional government was an important support, like the City Hall of Angra do Heroísmo here in Terceira. So I think in the end this was a big success. But again, this is the start. Please continue to engage. There are certain events that will happen in the year. I know that in July, there will be another event about Julia at MIT in Boston. And hopefully we keep this community and increase the community around Earth observation. So these are my final words. Thank you very much. I hope you can still enjoy here the Iceland. Maybe some of you have the opportunity to visit our Earth Observation Center here in the Terinov, and I know that the director of Terinov is around, also where we are placed. A big thank you to Terinov because he's our partner to many of our initiatives. And enjoy the weekend here in the Islands, and thank you very much.
So we close the session here. I just want to correct something. I forgot to mention Iga. Thank you, Iga, for an outstanding work and so much work, as everybody now who is here now. So we close the session. So if you are online, the video will go off now. And if you are here, let's go for lunch, and then we can resume for a half-an-hour session requested by you, where we're going to see what happened on the backstage during the week here.